Here we're going to look at a nice double integral over a triangular region. We're going to maybe not solve this in the easiest way possible, but we're going to exhibit a lot of nice techniques. And I think this is a nice and elegant solution. So here we've got the double integral over t, where that's our triangular region, of the natural log of sine of x minus y dA, where that's our differential area component. And the triangle is defined like this. So the hypotenuse is the line y equals x. And then along the x-axis, we're going from the origin to pi. And then along the y part, we're going from this x equals pi, y equals 0, up to pi comma pi. So we've got that triangular region. So the first thing that I want to do is do a change of variables. But we're not going to do a one variable change of variables one at a time, like in terms of writing this as an iterated integral. I want to do a two variable change of variables and use a more general change of variables type formula. Okay, so let's maybe do that. So let's define our change of variables by multiplication by a matrix. So we can do a nice linear change of variables here. And that's kind of obvious because here we've got x minus y. We'd probably like to set x minus y equal to one of our new variables. And we can do that like this. Let's say here we want our new variables to be u and v. And let's say we would like our u to be the same thing as x and our v to be the same thing as x minus y. So that means we need to multiply by the matrix 1, 0, 1, minus 1 times x, y. So notice that fits the bill. So here we've got u is equal to x and v is equal to x minus y, just by matrix multiplication. And maybe we'll define g to be the name of this transformation. Okay, next what we want to do is see what happens to the triangle under this transformation. And how we'll do that is see what happens to all of the vertices on the triangle and then interpolate what happens between the vertices. So let's see, I've got my origin already marked. So let's go over down here and write my UV plane. And notice the origin is going to get mapped to the origin, because if x and y are both 0, then u and v are also both 0. Now let's see what happens to this point right here. So this point right here, which is x equals pi and y equals 0. So notice if x equals pi and y equals 0, well, let's multiply this out so maybe it's a little bit more clear. That's going to go to the point pi, pi. So I'll go ahead and add that to my UV plane. So here's my point pi, pi, so that's in green. This point gets mapped to this point. Okay, now we've got one more vertex of this triangle to figure out what happens, and that's the point right here, which is the point pi comma pi. So x is equal to pi, y is equal to pi. So let's see, that's going to get mapped to pi comma 0. So that means that's going to be this point down here, like that. So those are our three vertices of our new triangle. So essentially that's the same triangle. It's just been reflected in a certain sense. Okay, so let's maybe draw this triangle in here like this. Maybe we could call this triangle T prime so that it has a similar notation to our old triangle, like that. So now we can rewrite this as the double integral over t prime of the natural log of sine of v, applying our transformation, because notice v is equal to x minus y. And we need one more thing for our change of variables, and that's the Jacobian. So here we need the absolute value of this thing, which is partial xy, partial uv, and then we have dA prime, where that's like our differential area component over here in our UV plane. Okay, so we're off to a good start. We just have to calculate this. But in order to calculate this, we need to invert this matrix right here. But if you look at that matrix carefully, you'll notice that it is indeed of order 2. In other words, it is its own inverse. So let's maybe put that here. So let's notice that we also have the vector x, y, is the same thing as the matrix 1, 0, 1, minus 1 times the vector u, v, which tells us that we have vector xy equals vector u and then u minus v, like that. Okay, great. And then let's recall what this object here is. So maybe we'll write it out. So this is going to be the double integral over our triangle t prime, the natural log of sine of v. Now we have the absolute value of the determinant of the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v. So that is the standard formula for change of variables with two coordinates. But it's not too hard to see that if we have a linear transformation like this, that matrix is in fact just exactly this matrix right here. In other words, the linear transformation is exactly the Jacobian before we take the determinant. So that means we can put a 1 here. This is obviously 0. Here we have this one is 1, and this one is minus 1. But then we also have to take the absolute value of this determinant that's built into the formula. So in the end, we get the double integral over our region t prime right here of the natural log of sine of v and then dA prime, where that's our differential area component in the uv plane. Now we can change this double integral to an iterated integral. So let's see, maybe we'll do the u integral on the inside and the v integral on the outside. So if we do the u integral on the inside, then that means we'll have du here and then dv. Well, what do we need to do? If we're doing the u integral first, then that means we need to go from this object right here, which is u equals v, all the way up to u equals pi. So here we're going to go from v to pi, and then here we'll go from 0 to pi to finish it off in the v part. And then we'll have natural log of sine of v. But now notice that this natural log of sine of v does not depend on u, but that means we can factor that out of the inner integral. So here we have the integral from 0 to pi of the natural log of sine of v, and then that's times the integral from v to pi of du, and then that's all inside of this dv integral. But this is a pretty straightforward integral. We can easily see that that's going to be pi minus v. So here we have that this is equal to the integral from 0 to pi of pi minus v times the natural log of sine v dv. So now let's maybe stop there on this board, bring this to the top, and then we'll move on. Okay, on the last board, we did a change of variables with two variables to change our goal integral, which was a double integral over a triangular region, to this single integral. So we've got the integral from 0 to pi of pi minus v natural log of sine of v dv. Now I want to do some sort of a trick. So what I'm going to do is write this as 1/2 and then twice this integral, but I'm going to write twice this integral as the integral plus itself. So here we've got the integral from 0 to pi of pi minus v times natural log of sine of v dv, and then plus another copy of that as well. So the integral from 0 to pi of pi minus v natural log of sine of v dv. And I want to point out that this is maybe like a final draft type solution, because this isn't some trick that you would come up with on the fly, but this would be maybe a nice way of writing it down after you already have a solution worked up. Next, I'll do a change of variables for each of these integrals, and I'm going to use the same variable for each change of variables, even though it's going to be a slightly different change of variables. So the change of variables I'll do here is just setting v equal to theta. But that makes dv equal to d theta. So essentially I'm just replacing every v with a theta there. And over here, I'm gonna set theta equal to pi minus v. But now notice if theta is pi minus v, then v is equal to pi minus theta, which tells me that dv is equal to minus d theta. But then something else happens here under this change of variables, because we'll have this object right here, which is sine of pi minus theta, but you can check that sine of pi minus theta is the same thing as theta. So that's how that changes. Then this guy right here changes just to theta. So that kind of motivated our whole change of variables there. But let's see what happens to the bounds of integration. So if v equals 0, then that's going to make theta equal to pi. So that's the change that happens here. And then if v equals pi, theta is equal to 0. Okay, good. So that means we can go ahead and write this sum of two integrals with the same variable, this theta variable, where we've done the change of variables like we just described. So here we're going to have a half, and then this is going to be the integral from 0 to pi of, this will be pi minus theta times natural log of sine of theta d theta. Again, all we did right there was replace all the v's with thetas. And now we'll have, well, let's maybe do this. Let's take this minus sign attached to the d theta and let it switch the order of this integration. So that's kind of a well-known thing that if you have a minus sign, you can switch the bounds of integration. So that's going to give us a plus the integral from 0 to pi of theta times natural log of sine of theta d theta. Great. So we've got something like that happening. But now let's push both of those integrals back together. And notice that when we push both of these integrals back together, this theta times natural log of sine theta will cancel this theta times natural log of sine theta. So we just have pi times natural log of sine theta. We can bring that pi out, and that leaves us with pi over 2 times the integral from 0 to pi of natural log of sine theta d theta, like that. So let's maybe go ahead and bring that up, and then we'll tackle this integral. We got our goal integral down to pi over 2 times the integral from 0 to pi of natural log of sine of theta d theta. This integral is on YouTube already from some other people, and including me in one of my older videos, but we're going to calculate it here for completeness. And we're going to present something which I would call, again, maybe like a final draft version of the solution, which is kind of a really filed down to exactly what you need and not like an exploratory version of the solution. Okay, so let's maybe go ahead and do that. So here's what I'll do now. I'm going to write this as pi over 2, and then I'm going to replace this integral with twice this integral minus this integral. So here, this is the same thing as 2 times the integral from 0 to pi, natural log of sine of theta d theta, minus the integral from 0 to pi of natural log of sine of theta d theta. Now, I'll take this guy right here and split it into two pieces, and that'll be the integral from 0 to pi over 2 and the integral from pi over 2 to pi. So that gives me this. I've got pi over 2, and then I'll have twice the integral from 0 to pi over 2 of natural log of sine of theta d theta, plus the integral from pi over 2 up to pi of the same function, natural log sine theta d theta, and then close those parentheses, which are being multiplied by 2, and then subtract the integral from 0 to pi of natural log of sine theta d theta. But now we're going to do a change of variables in this second integral. And I'm not going to name it a new variable because this is exactly the same change of variables we used on the last board, just over a different interval. So I'm going to replace theta with pi minus theta. And then let's recall that sine of pi minus theta is still sine of theta, so that doesn't change the integrand. That's just going to change the bounds of integration. So these new bounds of integration will be, let's see, from pi over 2 to 0. but then we pick up a minus sign from the d theta, and that can switch the bounds of integration. Okay, so let's see what that gives us. Here we'll have pi over 2, and then we'll have 2 times the integral from 0 to pi over 2 of natural log of sine of theta d theta. That's just bringing this guy down. And then by this change of variables here, we get the same integral again. So the integral from 0 to pi over 2 of natural log of sine of theta d theta. Close those parentheses. And now we're subtracting the integral from 0 to pi of natural log of sine of theta d theta. Great. Now we'll do one more change of variables on this board, and that will be for this integral. So for this integral, we're going to send theta to pi over 2 minus theta. And then sine of pi over 2 minus theta will be cosine. We pick up a minus sign in the d theta, and that changes the order of the bounds of integration. So we can change those back with the minus sign, and that transforms this into the natural log of cosine of theta. So let's see what that gives us. We have pi over 2 is out front still, and then we have twice, and then the integral from 0 to pi over 2 of natural log of sine theta d theta, plus integral from 0 to pi over 2 of natural log of cos theta d theta. Close the parentheses off of that multiplying by 2, and then we'll have minus the integral from 0 to pi of natural log of sine theta d theta. Okay, good. So let's go ahead and bring that up. On the last board, we ended up here. So we've got our goal integral is pi over 2 times this big object. We've got twice the integral from 0 to pi over 2 of natural log sine theta, plus the integral from 0 to pi over 2 natural log cosine theta. That's all multiplied by 2, like I said, and then minus the integral from 0 to pi of the natural log of sine of theta d theta. Now notice that these integrals are over the same domain, so I can smush them together. I'll have natural log of sine plus natural log of cosine, but I can use a logarithm rule to turn that into natural log of sine times cosine. So let's do that. So we'll have pi over 2, and then we'll have 2 times the integral from 0 to pi over 2 of the natural log of sine of theta times cosine of theta d theta, like that, and then minus the integral from 0 to pi of natural log of sine of theta d theta. Great. Now we want to use a trig identity. So there's a well-known trig identity that says that sine times cosine is 1/2 times sine of 2 theta. So I can take this and rewrite it as 1/2 times sine of 2 theta. So that, combined with the fact that we are still inside of a natural log, and I can reapply my product rule for natural logs to split that up into the natural log of 1/2 plus the natural log of sine of 2 theta, will give me the following. So I've got pi over 2, and then 2 times the integral from 0 to pi over 2 of natural log of 1/2 plus natural log of sine of 2 theta d theta, minus the integral from 0 to pi of natural log of sine of theta d theta, like that. So now let's start putting things together. So let's see what we can do here. We can take this 2 and this 2 and cancel them. So that's going to give us a pi times the integral from 0 to pi over 2 of natural log of 1/2 d theta. So I've split that integral up, and then I'll leave the pi over 2 out of the rest of it. So we'll have, this is going to be plus pi over 2 times twice the integral from 0 to pi over 2 of natural log of sine of 2 theta d theta, minus the integral from 0 to pi of natural log of sine of theta. Finally, we're going to do a change of variables on this integral. We're going to do that so we can make it look more like that last integral. So let's maybe here give it a variable name. So let's say we'll say phi is equal to 2 theta, but that tells us that d theta is equal to 1/2 d phi. So that'll be the change of variables that we do. But notice if theta is equal to 0, phi is also equal to 0. And if theta is equal to pi over 2, phi is going to be equal to pi. Okay, so let's maybe see what else happens here. So this is going to turn into a phi. This is going to turn into a 1/2 d phi. So let's do that simultaneously while making the change of variables over here, which is just phi equals theta. So let's see what that gives us. So I'm going to go ahead and finish this off. So this is just a constant. So we'll have pi times the length of this interval times that value. So that's going to be pi squared over 2 times natural log of 1/2 plus pi over 2. And then let's see what we're left with. So notice this 1/2 will cancel this 2, and we'll be left with the integral from 0 to pi of natural log of sine of phi d phi minus the integral from 0 to pi of natural log of sine of phi d phi. But this one is going to cancel with this one, leaving us with our final value, which is pi squared over 2 times natural log of 1/2. And that's a good place to stop.